Hello everyone, so welcome to week 2 of ENG 668 or 685 Engineering Modeling and Simulation. So hopefully by now you will have installed the software package, watched the relevant videos, introduced you to the module and the online teaching. So looking at week 2, what we're going to be doing is looking at the actual software itself now, going through ANSYS Workbench, Design Modeler, Meshing, ANSYS Fluent, Static Structural, and again there's going to be a little bit of a quiz on your understanding of the software and to submit some evidence of your workflow. So again, this is restricted, so this will be opened up on the 11th of May, or again if you progress through submitting work, you can progress through each of the weeks as given within your own time. So week 2, what we need to do first is download the evidence template. Once you've got the evidence template, fill in your name, the program that you're on, and this is where these evidence, they're not officially marked or anything, it's just a way of providing evidence that you have completed some of the workshops and the key elements. So have this opened up, and what we want to do is start watching, click on the video, and then obviously you'll see what I'm presenting today, which is the ANSYS. So what we want to do is press start, go and find the ANSYS R19 R3 folder, and if you go all the way down, what you will find is the Workbench 2019 R3. Click on this, and hopefully, fingers crossed, it will take a few seconds to load all the key elements and components and have the workbench open and ready. Now once workbench is opened up, what you will see is the analysis systems on the left hand side and component systems as well. If you don't see these, that means there is a license issue, so please just go on to the ansys.com and see how to resolve this problem. So first things, what we want to do is save our workbench, so file, save as, and what I recommend in your documents or somewhere, create a folder called ENG 668 or 685, so ENG 668, and just call this one week 2. Now the workbench is a platform where all the elements that's needed to conduct a certain analysis, being CFD or FEA, all the elements are available to be placed in one software. Previously, all key elements were done individually on different kinds of software, and there was issues with files being corrupted or files being lost, softwares being shut down, bought out by other companies. So what ANSYS has done is they've unified this workspace and provided all the elements that's needed in one package, which means all the files get put into one folder, and that way it's nice and safe. So again, looking at the whole process, we're going to be doing CFD and FEA. We're going to start off with doing a full system analysis. Now, the advantage with the full system analysis is it provides us all the elements that's needed to conduct one study. So if I grab, for example, the one that we'll be using is Fluid Flow Fluent. If I click on this, left click on it, a green box appears, meaning I can drag this and drop it into this section here. Now, as I said, it's got a geometry component, it's got a mesh component, setup component, solution, and result. If I wanted to do this as an individual element, and you guys can have a go at doing this, so I can drag a geometry, and then obviously I need a mesh to go with the geometry, so I can then just grab a mesh element, and what I will do is drop it onto the geometry. Then I need a setup and a solution, so I will go to a Fluent, drag and drop it onto the mesh, and then obviously a result to go towards the end as well. There we go. So the advantages and disadvantages obviously are different. So for example, I can have the same geometry, I can have 2 or 3 different types of mesh to do some analysis, or I can have a different kind of solver added to this mesh. So for example, I can say here, I'll take the same mesh, but I'll run 2 different kinds of turbulence models, and then I'll have a look at the results. So there's many advantages of doing individual components, but the advantage of using a full system analysis is it's all compiled all as one, and you can name and do everything that needs to be done. In order to, for example, just say that this got broken, or you dragged and dropped it and you forgot to connect it, it's very simple to select the setup, select the solution, select the mesh, and you can drop it onto the setup that way and reconnect them. Or obviously, right-clicking on these will also delete what's needed. So for example, if everybody can just delete these, we won't need them. And here, you can rename these. So again, give them whatever name that you want, week 2. And if you need to move them as well, if you have multiple ones, for example, if I just put a static structural here, I can then move these anywhere that I need to move them, and using the roller button, you can zoom in and zoom out as needed. Okay, so what we want to do, everything is saved. You can save in multiple parts. You can save here, or you can save in an individual component. It doesn't really matter. But the key thing is try and save as you go along at multiple points. So first things first, most important, right-click on geometry, and the default is Space Claim, which is a new package from ANSYS. But what we want to do is we want to use Design Modeler. Space Claim is quite powerful in its sense that it requires a lot of RAM and high-spec PC components. But the Design Modeler is a nice sketching 3D CAD tool, which is useful in any kind of computer package. So new Design Modeler, geometry. Once this opens up, you can change the format. Here I've changed my background into white. You can easily do that by going into the tools options here, and in the appearance. So for example, I put white here. You can change it to any color that you want. So let's go back to Design Modeler. Now here we've got some very important toolbars. We've got a tree which records all the steps that we're doing. We've got the sketching pad, the modeling pad, and then up here we've got our selection tools. So selecting a point, selecting an edge, face, volume. Very important when you look at the tutorials and when you're selecting certain surfaces. So you may be trying to select a surface, but it's not allowing you to do this, is because your tool selection is selected to something different. So always keep an eye on that. Obviously you've got the rotation, zooming in, zooming out, pan, look at surface, and then there are many tutorials that you're going to be going through, which will go through all of each steps, but this video is just to give you a quick overview. So what we want to do is look at XY plane, look at, and that just brings it into our view. We want to go to the units and change it to millimeters. Now what we're going to be doing here quickly is just doing a square rectangular box section, and this is going to be our wind tunnel, and in that wind tunnel we're going to be placing a pole, which is then going to be forced with a velocity of 100 meters per second coming on, and the pressure forces on that pole is then going to be transferred as a boundary condition to an FEA analysis, so we can do static structural to look at the deflection. So quickly, 2 ways of doing this. We can either draw a sketch or we can use primitive shapes. I always use primitive shapes to make your life a lot more easier, but as I said, this is just a quick overview. We'll do it both ways for this time. So new sketch, sketch 1, go to the sketching tool, draw a rectangular box. We always want to make sure that the center is always in the middle. It doesn't really matter how you do it, but always make sure the center is in the middle. We're then going to give it some constraints. We're going to use the symmetry function. So with the left mouse button, select the y-axis. Then with the right mouse button, click and select. So once that's selected with the left mouse button, then select the left edge, the right edge, and that's now symmetrically constrained. New select axis, select the x-axis, upper edge, lower edge, and that's now constrained. Press escape on the keyboard and it will release that function. Now give it a dimension. So use the general, click up, left, and here we want to put 1000 millimeters by 450 millimeters, and that's the size of our wind tunnel. Now if I use the middle roller button, I can zoom out, or I can just press this button here and it's the look at face plane and it just brings it into view. So again, this is the size of our wind tunnel. Now very easily I can now just go to the extrude, and I can extrude this sketch 1, press apply, add it as material, and it's going to be 225 or 450, 225, and it's going to be both symmetric, so it's that way there, and then press generate, and now it's created a box, rectangular box, which represents our wind tunnel. So that's one method of doing this. So if we now just go to create primitive box, and again you can see the box system is very simple. So the X is going to be 1000 millimeters, Y is going to be 450 millimeters, Z is going to be 450. But obviously here, that's the point of origin. We just need to centralize it. So in the X, it's going to be minus 500, and you'll see it starts going in, minus 225, minus 225, and this time we're going to add it as frozen. Now the difference between add material and add frozen is, if I add this as material, it will just unite with the original box that's there. By adding it as frozen, it keeps it as a separate entity. This way, then the separate entity can be rotated, altered, geometry function parameterized. So adding material and adding it as frozen are two ways of keeping the bodies absolutely separate. So if I press generate, you will see there's two solid bodies. Now if I did go ahead and add this as material and then press generate, you'll see there's only one body because it's automatically united with the previous body. So all we want to do now is just right click on that box and press delete, as we'll just use the original box that we have. Now we want to make sure that this is fluid, as wind will be used as our main fluid, and we just call this WT wind tunnel and just press generate. Now I always work with wireframe, so in order so I can see what's happening inside that sketch, I can just hide sketch so we can see what we're doing. And what we're going to do now is we're going to create a pole of some sort, or a bar of some sort, which is going to go to the bottom of the wind tunnel and come up halfway, and that way there, when the air goes in, it will hit that plate and it should bend over due to the forces. So what we're going to do is we're just going to use primitive shapes. So create primitive box section. Now we know it needs to be 225, but what we're going to do is we're going to put minus 225 there, so it goes behind. Now obviously we don't want it all the way, so let's say it's going to have a Z of 100. Yep, that should be fine, and a thickness of say 2 millimeters. And that's going to be a nice plate that sits in the middle, that's going to be affected. Now because it's 100, we just want to make that one minus 50 so it sits in the middle. So obviously if I add this as material, it'll just disappear, it'll just be combined with this one. So what we want to do is we want to add it as frozen, generate, so it becomes two separate bodies. And now, as I said, for ANSYS CFD, we want to subtract this cylinder, this plate from this volume, leaving us an empty void. So therefore the air coming in obviously cannot travel through an empty void, so it has to go around the shape that is being subtracted, because this whole volume will be filled with mesh, and that mesh is where the calculation will take place. But at the same time, because we're going to be running an FEA analysis, we don't want this plate to disappear, so we'll be using a Boolean function to subtract, but also retaining that actual shape or body. So create Boolean. On here we're going to select subtract. Now anything that's yellow requires human interaction, so it requires us to either select or highlight some elements and then press apply. So the target body here is obviously the wind tunnel itself, and the tool body is going to be this last solid here. Now when we press apply and we want to preserve the body, because if we don't preserve it, it will disappear. So yes, we want to preserve it, and generate. Okay, so if now this one is a solid, I'm going to call this one the plate. Now if I suppress this, so it's just hidden for a bit, so you can see now we've got a volume where the airflow will come out around the shape, because the actual plate has been cut away from this element. So to give you a better view, and again this is the best time to have a look at what the mouse control is as well. So what I would say is the middle mouse button spins your model, the roller up and down zooms in and out. Now if you use the keyboard as well, so control left click is multi-select. You can see here where I'm selecting the faces, because I've got faces turned on. At the moment, if I do it that way, individually I can't. Press control and it can multi-select. The right mouse button, again, left top hand corner to bottom right hand corner zooms in. And then obviously if you press H on the keyboard, it just brings it back into view again, and if you press the face look at, and it brings it back to your pan view. So what I want to do is I want to cut this in half just to show you guys that the model has been subtracted from this volume. So if I make a cut plane there, go back to my views and look at it as a shaded exterior, you can see that the plate has been subtracted from this volume. So as I said, all of this will be filled in with a mesh element in the next stage, and this is what's going to be calculated afterwards. And then obviously if you unsuppress this, and then to come back out again, just unselect that and brings it back into your view. So view, wireframe, that's what we want there. So this is the best time to either click on the ISO button and take a screenshot. So what we want to do is, it hasn't got a screenshot on this one here, but here if you just print your screen, what I'm going to do is I'm going to use the snippet tool, which is the Windows button, and press Shift and press S. It brings up the snipping tool. I can take a picture of that and then go into my word elements, and so obviously this is the design modeler part. So what I will do is Control V, paste that there, and that's my evidence that I've created this part here. So what's going to happen next is we're going to then make sure that this is fluid, this is solid, press File, or you can press Save here. As I said, you can save within each individual element, or you can save outside in Workbench itself. So press Save, press Save, and that's saved now, and File, Close Design Modeler. So what we want to do now is make sure that it's got a green tick. When it means it's got a green tick, you can move on to the next step. If it hasn't got a green tick, that means there's some errors. Like for example here, now it's telling you to refresh, ready for the next one. So double click on this. Keep an eye on down the bottom. It's just telling you it's starting ANSYS meshing. So you've got to give it a bit of a while, and it takes a bit of time, and then the ANSYS meshing will load up. And once this is loaded up, I always make sure that my units are in millimeters and kilograms per second. So straight away you'll see your geometry, and the key thing here is because we're going to be running the CFD first, so we only need the fluid element part of this simulation. So where it says plate, we can right click and we can suppress that body because we don't need it for the simulation. And here we should just have the wind tunnel. We've also got the coordinate system, and we've got some contacts which have disappeared now because we've suppressed the plate. So again, up here we've got the geometry features, we've got some display features where we can look at our meshes, and we've got selection tools as well. But the key elements here is leave it on the home, but these are the elements that you need. So again, just very similar to the design modeler, we've got vertexes, edges, faces and volumes. So whilst there's no mesh on this model, it's the best time to actually select faces so we can give it a name selection. So what a name selection means is we're defining what that face represents in the fluid dynamics part of the package. So again, the mouse key buttons are exactly the same. Middle mouse button rotates. Press Control and the middle mouse button pans out, zoom in and out. So what we want to do is select this surface, press N on the keyboard, and a pop-up will come up, and we want to call that one Inlet. And it's very important that you correctly spell all the name selections, because the algorithm looks at the terminology and defines the boundary condition. If there is a spelling mistake in Inlet and you transfer it over, the Fluent part won't recognize the name and therefore will have it as a default wall, which can have a huge problem on your simulation. So Inlet, the back end is Outlet. And again, here we have to use the multi-select tool. So Control, top surface, side, rotate, middle. So 4 surfaces selected. Press N on the keyboard, and these are our wall. Again, there should be a panning tool which can bring it back in again. And what we want to do now is obviously we want to grab the inner plate, and the inner plate is going to be a bit of a hard time because obviously you've got these surfaces that are in the way. So the best thing to do is grab these 4 again. And what we want to do now is press F8 on the keyboard, and it will hide those faces, meaning we have access to these. Okay, now obviously there's quite a few faces here. You can individually grab them, but what I want to show you is the box tool selection. So again, in the mode up here, you've got box select, and you can select a box and it'll grab all of those. Obviously now to go back, you have to go back to single select, otherwise it will always be box select. Now there is a quick shortcut for this. I'll try my best to explain. On your mouse, if you hold down the right mouse button, you'll see the plus sign come up, and then whilst holding the right mouse button, left click as well, and you'll see it toggles through the box select and single select, which is a unique way of doing it much quicker. So select all of those, N on the keyboard, plate. Once that's done, go back to single select. So open up your name selection, Inlet, Outlet, Wall, Plate. Nice and simple. Obviously we need to define the fluid, so WT, right click on that, create name selection, air. Okay, so all the name selections done. Now is the best time to do the actual mesh side of it, and again there are many tutorials that will go through all the stages of the meshing. Again, this is just a quick overview. So right click on mesh, insert method, click on the body, press apply, and here we want to change it to tetrahedrons. Now there are many different kinds of mesh. The tetrahedrons, the most quickest, fastest, reliable mesh algorithm that's used. Once that's been selected, press escape, click on the WT so it's nice and view. And what we want big mesh everywhere else, but we want fine mesh down here. So the smaller the mesh around here, it means that there is a great importance when it comes to the simulation. So the simulation will focus around here with a more detailed calculation rather than the calculation up here, because assuming up here has no relevance on the effect of the plate. So mesh, insert, sizing, make sure we got the edge sizing tool selected, and then here click on that. Okay. Okay, H. And what we want to do is box select around this, and so maybe here display, for example, my view is a bit okay. So box select around those, apply, and you can see the element size. So the element size by default, it's saying it's 59 millimeters. So that circle on my mouse right now represents 59 millimeters. We're going to change this one to say around about 2 millimeters to give it a bit of sizing. For some reason, I don't know why it's done that. Okay. Okay, so much more smaller, 2 millimeters. Actually, go with 5 as it's a tutorial. We don't want to run with too much mesh, so say about 10, and it should be good. So now clicking on this mesh, we've got these are all called local sizing, and now we're going to go to the global sizing. Now again here you can see the default size is 59, and we've got 10 there, so let's change that to 20, and you can see it's got a lot more smaller. Sizing wise, it's not using adaptive, therefore you can capture curvature. Do you want to capture curvature? No, we don't. And we don't want to capture any proximity either. So let's just go down, capture proximity, no. Okay, so if you press generate mesh now, you can click on mesh up here, so you can generate mesh there, or you can just right click and generate mesh. And this is the best time to go back to display and view as wireframe, because inside you can see the mesh. Okay, so that's meshed now. Just quickly give you some how to get some statistics. So statistics wise, this is 120,000 elements. Again, the student license version restricts us to 500,000 elements, so we want to try and keep it below that. But if you are working on the university campus, this is there's no limit. It's limitless. But saying that, if you go more than 1 million to 2 million elements, the simulation time can run up to 2-3 hours, 4 hours, or even much more longer. So once we've done that, we're very happy with it. So file, close meshing, and you can see there's a lightning strike that's appeared. That means it requires an update. So right click, update. Now once it's updated, you'll see there's a green tick. If you don't get a green tick, or you get a green tick with a little X next to it, it means there's a problem within your meshing. Mainly it's to do with the name selection. So again, sometimes it happens where you selected one surface and you gave it a name selection, then by accident you've grabbed that same surface and you gave it another name selection. No surfaces can have two different name boundary conditions, so that's why it always gives you an error. And even when you go into the meshing, you can right click on the mesh and show problematic geometries, and it will show you what the errors are. So right click on setup. Once you click on setup, again, it automatically knows it's three-dimensional. We want to use no other options. Now the processing options. Running it on serial means your processor will distribute the processing power amongst your cores on your microchip processor. However, you can run it in parallel. Now, if you're running for example, an i7 processor, I can put 8 processors there, where it will now use 100% of my processor to quickly run the simulation. So the simulation runs quicker, much faster, because the geometry is split into 8 sections, and each core of the processor simulates and calculates for that section only. Where with the serial one, it's a little bit longer because the processors get distributed to the cores and they share and they alternate. However, if you run the parallel on your laptop, it can damage your processor because of the high intense calculations and the overheating conditions. So if you're in the universities, we always recommend running it in parallel, because the university L100 computers have been built for those kind of number crunching conditions. But on your own laptop, it's at your own risk. So here, I would run it in serial. So press OK. Now, once ANSYS Fluent opens up, there's many ways of doing this. You've got the outline view tree. You've got the tab method, where it goes through the domain, the physics, the user-defined solution, and you can do these kind of steps. So the tutorial packages that I've provided, the actual workshops, some use the ribbon, some use the tree. Try and get used to all of those. So our models come in. First thing, steady or transient. We don't want to run anything time dependent. It's very time consuming because it's all to do with time. But what we want to do is a steady simulation. So first of all, turn on gravity minus 9.81, because positive 9.81 is going upwards, so we want to go in a downwards direction. So always work with models, then we work with materials, boundary conditions, initialization, and then run calculation, and then these are all of our results that we're going to be using. So first things first, model. We know it's going to be a turbulent flow because it's 100 meters per second. So let's go to viscous, change this one to K epsilon model, and then you've got the different models, near wall treatments. Again, we don't want to go into too much detail about these. They are quite advanced, but what we want to know is just use the standard K epsilon model and near wall treatment. Once we got that, the material, we just want to make sure that it's air. That's absolutely fine, but in the air itself, we could potentially change the density and the viscosity like it will do in one of your assessments. So change and create, close. We've got solid, but we've got no solid interaction here. That's for the FEA package. Boundary conditions. So again here, inlet should be velocity inlet, outlet should be pressure outlet, plate should be a wall, and then the wall should be a wall. That's absolutely fine. So let's go into inlet. And as I said, we're going to use 100 meters per second, give it quite a bit of a speed there. Press OK. And the outlet should be 0 because we got no pressure at the end. So it's 100 meters per second coming in, going over the plate, and then we should see what's happening here. So after that, initialization. Now, hybrid and standard. Hybrid, if you have multiple inlets, very good with hybrid. Here we've only got one inlet, so the standard initialization is the best. So compute from our inlet, it will give us the speed, initialize, and then we run calculation. And here what we're going to do is we're going to put a number of iterations. So how many times should it calculate until all the key elements of the equation have reached a very good number of accuracy? So here, give it 1,000, the default value. If it's not finished within 1,000, you always give it more. But the graph, the next graph, is the key thing that allows us to understand if we're going in a good direction or a bad direction. So you can see here it's running quite slow. Obviously, if you're running it in 8 cores, it'll be a lot faster. So we can see here that everything's converging towards a downward direction. So what we want to see is we want to always make sure that the graph element is going in a descending format. Like you can see now, it's descending down. At any point, if it goes above the set line of 0, it means that there's a serious issue with the geometry or the mesh file. I would go back and see what's happening here. So this has been running for a while now. As you can see, it's gone up to 377 iterations, and here's a clear example that the mesh is not appropriate for this model, and we can see that the simulation is just fluctuating. And if it fluctuates like this, it means that it will take a long period of time for it to converge. And what we're looking for is the simulation to stop automatically within the given time of iteration of 1,000, and it should make a statement that the solution is converged. And you can see some tutorials or workshops that will actually display that. So if we just press stop on here, again, most of these take a long period of time to calculate. I would always recommend taking regular breaks and looking at the screen for a long period of time. So please do make sure you take regular breaks. So what we want to do now is have a look at our quick results. So before we go into that, so graphics, contours here. We can have a contour of images, so we can have a look at our pressure, we can look at density, velocity, turbulence. So we'll look at the pressure first, but to select the plate display, and we can see here, the pressure forces acting on the plate all the way around. Now, if we click on the Z here, and then go to create a surface plane, align with viewing plane, and then press create, close, we create this plane 4. So if I press display on that, it will show us a mid-cut view plane of our domain, and we can see now what's happening in terms of static pressure. We can look at dynamic pressure as well to see exactly what's happening, and at the same time we can also go to velocity and look at this as well in terms of where is the highest velocity, where is the lowest velocity, and these contour images are given a guide with the key feature here. So also vectors is another thing as well. So we can select plane 4, press display, and these shows us in arrow format. Again, zooming in, we can see clearly what's happening with the velocity with a big vortex behind. We can also press close on that, close on this, then go to path lines, and again here let's skip. The pathline skip is very good, so let's 100. If you've got a very good graphics card, you can leave that as 0, but if you don't, I would always start off with a value of 200, plain, press display. You can see what's happening there. So that's not too strenuous on the graphics. So let's change that to 100, display. Okay, let's go down a bit more, 20, display. So okay, so we've got something like this now. Again, if you click on the plus, now the path lines here represent, these variables just represent each line as a different color. We can change them to say velocity, magnitude, and now it represents that way. We can then go to continuous and press pulse, and we can see a quick animation of what's actually happening, of the airflow around this actual plate. So this is the ANSYS Fluent part done. So make sure you press stop, otherwise it crashes. So press close. File. What we want to do is go back to iterations quickly, because it hasn't converged. It may cause us a bit of a problem. So what we're going to do is go to run calculation, and we're just going to put in a value of 2 and press calculate. Use your settings for changes for current calculation only, and it will do, and it will automatically stop. So, and it'll press done, and it'll say calculation is complete. Press OK. Okay, file. Alright, sometimes it does this for some reason. If it ever does do this, what I would say is, if you right click on your taskbar, and this is a common problem, look for the CX1950 end task, and that will just close Fluent, which is fine. Okay, so now that we've come back here, sorry, forgot one thing about our evidence. I keep forgetting about this, so if you can just double click on the mesh. What we're going to do is grab a screen grab of our mesh element, and we'll go back into the solution. And this is a good example actually, to tell you which one to actually select and which one not to select. So once the meshing is opened up, we want to show the mesh. Again, click on the ISO button, zoom out a little bit. Again, take the snipping tool, okay, so new, move that out of the way. And we just want to take a picture of this. Go to our Microsoft Word, go in here, and then just Control V. Okay, and so now we've got that evidence there. It doesn't need to be neat, doesn't mean it's tidy, it's just some form of evidence. So close back, close your snipping tool. No, don't want to save. File, close meshing. Now, what I said before was quite important. So here you can see the lightning strikes come back on again, is because we've gone into the mesh, and now it believes there's something that's needed to be run. So if I click on setup, it'll go only into the setup. If I click on solution, it will go on to my results only. So what I want to do is I just want to have a look at my results. So on here, click on solution. Give it a few seconds. We're going to go to graphics, go to contours. Okay, so see here the mid-cut plane has disappeared again. So here, click on the Z, create plane, align with viewing plane, and then create, close. Click on that, display, and select velocity, magnitude, display. Now here, there's many ways of taking images. You can take a screen grab. I won't take a screen grab here. What I would do is right click on the top bar here. You click on the top bar there, copy to clipboard. Once that's copied to clipboard, go into your Word document, and here, Control V, and it pastes that image in there. Okay, so that's really good. It's got everything that we need at the moment. So minimize that, close that. We just want to basically run the calculation, not for 1,000. We just want put a value of 10 there, and press calculate. And just do 10 more. What we're looking for is that calculation complete. So rather than having a lightning strike on our workbench, we'll have a green tick. So again here, okay, you may press OK, File, Close Fluent, and it will save everything that's needed. And here you've got the solution refresh, that's not a problem. What we want to do now is grab a static structural and drag and drop on the solution. And once you drop on the solution, you can see that the geometry and the solution are both selected, and press yes. Now in here, all you want to do is just refresh this, right click and press update on that. And it's important to have a green tick here, otherwise you won't be able to select the key elements needed for the boundary condition on this end. And as you can see here, all it's doing is just giving you some information that it's loading the mesh, it's initializing, and it's solving. And remember, we put a value of 10 before, and because of that 10, it's only going to do 10 iterations. Where if it was 1,000, it will do all 1,000 iterations, which will take a long time. But again, the tutorial packages will show you how to do this. So once in the model, double click. Again, look at the bottom left hand corner. It takes a bit of a time for the key components to open up. So here, again, it brings in both models, but this time you can see there's a question mark. So it's kind of knows that you've brought in an element which is actually fluid, and it's asking you what to do with this. So right click and we suppress. We don't need this. We only need the plate. And you can see by selecting the plate, the assigned material is structural steel. And you can bring in different kinds of material, and we'll be going through the material in a section. So if you just minimize this, the engineering data, click on that, engineering data, and here you can see the structural steel. It's got all the elements where you can change, for example, the Young's modulus, the Poisson's ratio. You can add different kinds of material as well. So for example, let's try one. So let's go into the general materials and let's bring in polyethylene. So click on the plus, and we've got polyethylene in our library now. So what we will need to do is, because we added this after we've opened up static structural, we'll have to click back on project. Once we've got mechanical, the polyethylene, you can see it's not here. So just quickly close this one down, click on model, press yes, because it needs to bring in the new material, and we'll bring that in. Okay, so here now we've got plate, structural steel, or we can change it to polyethylene. So let's leave it structural steel for the moment. We're going to give it a mesh. So just right click, generate mesh. And this will be the most generic mesh that it does. So element size, let's make that 2. Generate mesh. So it's a bit more smaller. However, we do need to look at the number of nodes, and I believe that's exceeded the student license element number, which is 22,000, I believe, or 29,000. I think it's around about the 30k mark. Let's leave it as it is, and then let's see if the software tells us if it's not. So static structural, what we want to do, again, on the top, it's got your key components, very similar to the meshing. It's got the units, which is automatically millimeters, and you've got the environment tool. So the environment tool allows us to apply forces and supports. So what we want to do is we want to apply a support on the bottom surface. So if we go here, support, fix support, select that surface there, press apply. So we've got a fixed support on there, and you can see this import load now. So right click on that, insert pressure. What geometries do you want to apply it on? So we want to apply it on all of the surfaces apart from the bottom surface. So again, using the control key mouse button, and that should allow us to do it. 5 surfaces, that's correct. CFD surface, which one? Is actually the plate. So now there is no OK button. You've got to press enter on the keyboard, and it selects plate. Right click on that and import load. And what it will do is it will import the load from the ANSYS Fluent onto this one here. As you can see, it's imported the pressure loads. Now, solution wise, we want some total deformation. we want some stress, say for example some equivalent 1 missed stress, and we want the error as well, because that will tell us if the mesh is correct or not. Now press solve, and I believe it should, yes, it will have a message saying that your product license has a size limit. So click on the mesh, change that to 5, solve, it will quickly mesh it, that will reduce, and now you can see it's running. So total deformation, we can see here clearly, that it is being deformed. You can play a bit of an animation if you wish to see. And the deformation is around about 4.8 millimeters. Structural stress, structural error, you can see that. Now, for example, if you go back on, now the structural error is important. What we want to do is we want to eliminate the structural error. And so here is clearly showing you that here there are some numerical errors. So you would refine the mesh here. So again, refer to the workshops which looks at refinement for mesh. But here it's just a quick overview. Now we can go back to the plate and we can change that to polyethylene and press solve. And what it will do now is it'll quickly run the simulation for polyethylene. And now you can see it's obviously the deflection is 828.98 millimeters, which is quite a lot. But again, it's just here, just showing you how to run the FEA side of things. And again, let's take a quick screenshot of this. So again, I'm just going to use my snipping tool. You can either do it this way, just for the purpose of this, or again, I believe you can go copy the image to clipboard as well. And what we want to do is static structural, Control B. We've got that one there. That's excellent. And then obviously in the mechanical here, there are some other tutorial packages of how to create line paths to get graphical data. Again, we will work through those in the work packages. So file, close mechanical, and the last thing that we need to do, make sure we press save, and we just want to take a snippet of our project screen, go back to Workbench, go to the first one, Control V, and there we go. And so there's all the evidence that was done in order to conduct this work package flow. So obviously all you do is file, save as whatever you need to save it as in your Workbench, and then go back to Moodle and submit your evidence. Okay, so I hope you enjoyed this video, and now what I would say is go to week 3, which will look at the design modeler. Again, there is a quick video here showing you how to set up some of the workshops, because some are creating geometry, some are importing geometry. So again, have a look at this. Thank you for watching.